Hello everyone. In this video, we're going to look at a method of approximation, okay? A good one, known as a slope field. And slope fields are very good tools for visual, what I like to call visual approximation. Okay, and what a slope field is really good at doing, a good slope field, and it tells you what our solution curve looks like. And the solution curve is the graph of our particular solution. So I would revisit particular solution. So a particular solution is a solution to the differential equation that passes through a certain point. So it's particular. There's only one solution that satisfies both the differential equation and passes through a point. That's known as your initial condition. And slope fields are very good, if drawn correctly, of visually seeing how the solution curve looks like and how it should appear. Okay? And slope fields are not that hard to make either, although really good ones are usually drawn by a computer. But it is not hard to make a basic one by hand. Okay, and we'll make one, and in the process, we'll learn about how good slope fields are for approximating. So first you need some axes. Okay? So it's our y-axis and it's our x-axis. And now what we're going to do is try to build a slope field for the function dy dx equals y. Okay? So we'll start an easy one. So first let's label our graph. Okay, we'll make it a lot easier. So 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. We have -1, -2. We have 1, so -1, -2, -3, -4, and -5. Okay. We'll label up to 5. So at 0, 0, okay? Make our slope field blue. Actually, make it red. So 0, 0, what does the slope look like? Well, in order to find out what the slope is at that point, you look at the y-coordinates, since the differential equation only asks for y. So at all points with y-coordinate 0, because for this differential equation, the slope only depends on y. So for all points with y-coordinate of 0, you get a slope of 0. So you would draw a small line segment with slope 0, or a horizontal line segment. So you have a small line segment. Now what about for 0, 1, or 1, 1, or any point with y-coordinate 1? Because the differential equation, the derivative, only relies on the y-coordinate, every single point with a y-coordinate 1 will have a line segment with slope 1, which is sort of like a 45-degree diagonal line. The same can be said about -1. Every point with y-coordinate -1 will have a slope of -1. And we keep on building the slope field, and you can start to see what looks to be some sense of what the shape is. So you can't really tell from the slope field itself what the shape will look like. But once we get there, I will explain how the slope field really helps, okay? So as you can see, start up to 4. So remember, these are just approximate, okay? These are not slopes of exactly 4. Okay, but you can still see a general pattern. Okay, so we have a pretty well-drawn slope field over here. Okay, and let's just draw 5. So we get all these points down. Okay, so we have a pretty good slope field drawn here. And what can we do with this in the first place? What do we do with it? Well, let's say I want to draw the solution curve through 0, 1. Okay? So this is our point. I'm labeling blue. I'm going to draw the solution through that. Well, you can kind of play a game, sort of connect the slope segments. Okay, so you want to draw your curve such that the slope at that point is pretty much equal to the slope segments around it. Okay, so this will have a slope of 1 at this point. Then you should curve it so that over here has a slope of 2. And over here is a slope of 3. Over here is a slope of 4. Over here is a slope of 5. Now, you have to remember that the slope field can be a lot more detailed than this. For example, I can have 1/2 slopes, okay? I can have 1/2 slopes because for all the points I have coordinate 1/2. So you can see there's not 1 and then 0, but you have to account for all those different slopes beneath it. Okay, so you can start to see a pattern here. And this graph should look very familiar, okay, from our discussion last chapter. This looks suspiciously like the graph of y equals e to the x, which is, in fact, a solution. You can verify that it's a solution using the techniques we did last video. Okay, y equals e to the x. And I did remember saying that it is the only non-constant function that such that the derivative equals itself. The constant function is actually represented here as well, and is simply the solution curve through 0, 0. If we had the solution curve through 0, 0, then we would have that constant function, y equals 0. And technically, the derivative of y equals 0 is the exact same as its function. And you see that from this graph. Okay, but however, you can use slope fields, okay? And if I were to draw a solution through, let's say 3, 2, well, you would start here and sort of draw the graph such that at each point the slope is the same as the slope segments around it. Okay? So with a better slope field, you get better and better representations for the solutions. Okay, so see how for that purple one I wasn't sure where it would go? That is because my slope field, even as detailed as it looks, is not detailed enough for solution over here, or maybe over here, okay, or maybe over here. So you can just make sort of approximations. Okay, this is an approximation technique. However, it does give you a very good way of finding out how a graph would be represented visually. So let's do another slope field. Okay, we're going to construct another slope field. Let's construct the slope field of dy dx equals x plus 2y. So this one's a harder example, okay? Since, oops, okay. So let's do a better example since the slope depends on both x and y. So this one's a bit trickier since we can't just do the easy way out as we did before. So slope depends on both x and y at this point. So it would help to make like a table of some sort, okay, or chart for several points. If you're given few points, they usually give you very few points if they ask you to draw a slope field on the AP exam. Okay, they have done that in the past, asked you to draw slope fields. Okay, and draw solution curves through them. So this is a skill that is quite important. So let's start drawing our slope field. So let's look at the case where x equals 0. So if x equals 0 and y equals 0, then our slope here is 0. Now if x equals 0 and y equals 1, okay, so you have 0 plus 2 times 1. If x equals 0 and y equals 1, you have 0 plus 2 times 1. Okay, and that's 2. So 0 comma 1 is you have a slope of 2. Now, for if x equals 0 and y equals 2, then you have a slope of 4. And you can sort of construct patterns that way. Slope of 6, slope of 8, slope of 10, which I'm making a very near vertical line. Okay? Now, for this, you can employ a similar technique. For y equals -1, since x is 0, then this will be -2, -4, -6, okay? So you can kind of use patterns, okay? Now, what about x equals 1? Okay, if x equals 1 and y equals 0, okay, let's look at the general condition where y equals 0. So we're going to do y equals 0. If y equals 0, then the dy dx will just be the value of x. Okay, so this will be have a slope of 1 if y equals 0, slope of 2. You can't apply this for all of y values, but just y equals 0, because it makes that right term equal to 0. So slope of 4, slope of 5, slope of -1, slope of -2, slope of -3, slope of -4. Now at y equals 1, okay, at y equals 1, you have, if x equals 0, if x equals 1 and y equals 1, you have slope of 3. Okay, if x equals 2 and y equals 1, you have a slope of 5. If x equals, you have a slope of 4. And for x equals 3, you have a slope of 5, 6, 7. Okay, at -1, you have a slope of -1. You have x is -1 plus 2 times 1 is 2. -1 plus 2 is 1. Okay, and at x equals -2, you have -2 plus 2, which is equal to 0. And at x equals -3, you get -1. Okay? So usually they don't ask you to make huge slope fields, okay? So I guess you can stop there. No, we should do a little more, okay? Okay, it's good to have a more accurate graph of slope. Now let's do y equals 2. We're going to go by y value. Now y equals 2, okay? We're basically having y equals 2, we're basically having the equation dy dx equals x plus 2. x plus 4, because 2 times 2 is 4. So we're basically making a new differential equation that deals only with the variable of x. Okay, so it makes it a lot easier to draw our slope field. Okay, so for example, this is 5, this is 6, 7, 8, 9. For -1, -1 plus 4 is 3. This is 2. This is 1. This is 0. This is -1. Okay, so now for y equals -1, you have dy dx equals x minus 2. Okay, 2 times -1 is -2. Okay, so if you have x equals 1, this will be -1. Okay, this will be 0, 1, 2, 3. And this will start to have much more decreasing slopes. And now you can start to see the slope field starting to assemble. Okay? You start to see the slope field starting to assemble. And you might now see some solution curves. So like this. Why don't you do that in blue? It's like something like this. Or through here. Or this. But you're not sure what it is though, okay? Since this is only an approximation. So you can, if you do it really accurately, you can see the graph right near it, okay? But you need a really accurate slope field, okay, in order to draw a good solution curve. If they ask you to draw a solution curve, they usually have a very accurate slope field, so you don't have to rely on, guessing what the shape of the graph will look like. Okay, next video we'll talk about how to actually solve a certain type of differential equation and its applications. Okay, so until then, thanks for watching. Make sure you like this video and subscribe, and comment below if you have any questions. Thank you.